Okay, let's dive in. We got some really fascinating source material here.
Yeah. What are we looking at?
It connects two things you might not immediately link. Calculus specifically, differentiation and integration, and, well, food security.
Ah, interesting. So math and making sure people have enough food.
Exactly. The sources you shared really zero in on how these calculus tools help estimate something vital, crop yield.
Right. Taking it beyond just the textbook equations, it shows calculus, in action.
Tackling a huge real-world challenge.
Precisely. The material explores how differentiation and integration give us a framework, a way to quantify how much food a field or maybe a whole region might produce over a season.
And this deep dive, it's really tailored for you listening, someone who's maybe grappling with these calculus ideas and wants to see them work outside of class.
Especially in this context, estimating total crop yield.
Yeah. So our mission basically is to unpack what these sources say about using calculus for that specific essential purpose.
Makes sense, because when you think about estimating total yield, you're dealing with things that change, right?
Constantly.
Yield doesn't just poof appear fully formed, it grows over time. And it can be different across a field too. Soil, sunlight, all that stuff.
Sure.
And the sources show how calculus helps manage those dynamics.
Okay, so break that down a bit. How do differentiation and integration fit in? Differentiation.
It's usually rates of change,
Mm.
like how fast something's happening right now.
Exactly that. Differentiation comes into play when you want to model the wheat yield is building up.
Okay.
Maybe day by day or week by week. You could use sensors, maybe satellite data, to estimate how fast crops are growing at different points in the season.
Right.
That growth rate itself can be a function, mathematically speaking, a function of time.
Uh-huh.
Or similarly, you might use differentiation to see how the density of the yield changes as you walk across a field, the rate of change per square meter.
Ah, okay, that makes sense. So differentiation gives us the snapshot, the instantaneous change or the point-to-point variation. Pretty much. It details the how fast or how different.
But getting the total yield for the whole season or the whole field, that's about adding it all up, isn't it?
Exactly. And that's where integration steps up as the really crucial tool.
Yeah.
That's what your sources highlight.
Right.
If you can model that rate of growth over the season using differentiation.
Which we just talked about.
Integration lets you sum up all those tiny instantaneous rates. It finds the total growth, the total yield, collected over the whole time period.
Like finding the area under the curve of that growth rate graph.
Precisely. Over the time of the season.
Okay, interesting. But it's not just time, is it? The sources mentioned integrating over area, too.
Yes, definitely. That's another key application they bring up. Yield isn't perfectly even across a field.
No, never.
Higher here, lower there. So if you can model that yield density, like kilograms per square meter, as a function of where you are in the field,
Okay.
integration lets you add up the yield from every tiny patch of that area. That gives you the total yield for the whole field.
So it's adding up across space, not just time.
Correct. It's integrating a function, maybe of two variables like x and y coordinates, over a defined region, the field.
Okay, so putting it together based on these sources, differentiation helps model the details, the rates, the variations.
Okay.
And then integration is the powerhouse tool that sums up all those details. It gives you the big picture number, the total harvest.
Yeah, it turns those continuous changes or spatial differences into a single, really useful total figure.
And that's a really concrete application, isn't it? It shows these concepts from calculus class aren't just abstract exercises.
Not at all. They are fundamental tools for tackling huge practical problems. Estimating the food supply, ensuring food security, that's pretty significant.
Absolutely. So the core takeaway here from reading this material is that while differentiation models the rates and changes,
Which is important groundwork.
integration is specifically identified as the, quote, suitable formulation for getting that overall figure, the total crop yield. Summing it up over the season or across the field area, that's the key for food security estimates.
It's a really clear example of calculus at work. Differentiate for the details, integrate for the total. Applied directly to a vital issue.
So for you listening, maybe think about that concept. Integration as the tool for calculating accumulated change or total value. It makes sense that it's the right fit for adding up yield over time or space, right? It's about summing infinite tiny pieces to get the whole.
Yeah.
What other real-world processes, things that build up or vary continuously, could integration help us measure or, understand the total picture of? Something to think about.